Hey there, so today we're going to take a look at absolute convergence and the ratio test. So in a recent video we looked at alternating series, and let's just refresh real quick on what that was. An alternating series is a series whose terms alternate in sign, positive, negative, and we generally say that an alternating series has the form -1 to the n minus 1. I'll go ahead and put my indices in here as well. N equals 1 to infinity is generally our starting point. So an alternating series can be written this way. A sub n is an alternating series if it can be written with an alternating factor. And then B sub n is basically going to be the actual, positive terms of the sequence, series. Well, a sequence, but then we're adding them all together to create a series. So we looked at alternating series recently, and we saw that it actually doesn't take a whole lot for an alternating series to converge because of the fact that it's adding and then subtracting and then adding and then subtracting and then adding and then subtracting. And so it's more likely for an alternating series to converge than it is for a series that has all positive terms. So in order for an alternating series to converge, we learned the alternating series test, and that said that an alternating series converges if three things. If the sequence B sub n needs to be positive, and it needs to be decreasing. So I'll number these. And then it also needed to have its limit approach 0. So that's all we needed in order for an alternating series to converge. So we're going to look at another definition today, well, two, I guess. One of them is absolutely convergent. Okay, so a lot of times when we are looking at an alternating series, we can state whether it converges or not, but sometimes we can also go a step further and state whether it converges absolutely or converges conditionally. So what these two terminologies mean, a series A sub n is absolutely convergent if it's basically if the series of its absolute value of terms is convergent. So basically it doesn't have to be an alternating series, but most of the time we use this term to describe an alternating series. That is, an alternating series can converge, but what if I took away that alternating factor? Does the series still converge? And if that's true, then we would say that that series converges absolutely. If we were to look at a series, again, most of the time it's alternating, but it doesn't have to be. If we look at a series, then we say it's conditionally convergent if the series itself is convergent, but the absolute value is not convergent. So basically this would be like saying, if it's an alternating series, this would be like saying that the alternating one is convergent, but the non-alternating one, if I take away that alternating factor, then that one would not end up being convergent. Let's go ahead and take a look at an example. And a great example to look at is the alternating harmonic series. So we're going to determine whether this alternating harmonic series is absolutely convergent, conditionally convergent, or maybe it's divergent. And actually, when we looked at the alternating series video, we already know that the alternating harmonic series is convergent. So we already know that from a previous video. But now we're going to take it, that one step further and decide whether it's absolutely convergent, conditionally convergent. We know it's not divergent because we have already established that the alternating harmonic series on its own converges. So we know that that's not going to be the case. So in order for it to be absolutely convergent, what we would need to have happen is that the series, we would need the absolute value of the terms. If this series converges, then we can say that the alternating harmonic series converges absolutely or is absolutely convergent. You can kind of say it either way. So if we take the absolute value of all of the terms, what we're essentially doing is removing the alternating factor, and now we no longer have the alternating harmonic series, but we have the harmonic series, right? So if you were to think about this factor here, it's either going to be -1 or +1, -1 or +1. So when we take the absolute value of it, it's always +1. So it's always going to be +1 over n. And we know that, we don't need to worry about the absolute value of n because n is going from 1 to infinity already. N is already positive. So that's why we can kind of like almost simplify that factorial. absolute value. So notice then that the absolute value of the alternating harmonic series, again, is the harmonic series. I wanted that to be a different color. The harmonic series, we know that diverges. And, you know, it's either something that we remember, like it's the harmonic series kind of notorious for diverging. But, you know, you could also justify it with saying that it's a P series with P equal 1. So that's the one reason why it diverges. So since the absolute value of the series diverges, but it's been recently shown that the alternating harmonic series converges, then we would say that the alternating harmonic series converges. Well, I'll say is. You could say converges absolutely, or you can say is absolutely convergent. I'm using the absolutely convergent terminology just because that's kind of how it was phrased up here, but it wouldn't be wrong to say converges absolutely. Oh, sorry, not absolutely. Conditionally, is conditionally convergent. Sorry, I got kind of stuck in our new definition there. It's conditionally convergent because the absolute value one diverges, but the alternating one converges. I also want to point out that in a recent video, we looked at the alternating harmonic series, and we had -1 to the n over n as opposed to -1 to the n minus 1. So just a little reminder that, you know, both of these are alternating. They're both the alternating harmonic series. The only difference between these two is that this one here that I currently have circled, this one would start its first value at +1, and then this one would start its first value at -1. And so both of these alternating series would converge. It's just that this one would converge to a positive value because it would start at +1 and then subtract something smaller and then add something even smaller and then subtract something even smaller. And then this one would converge to something that is negative, because it'd be -1 and then you would add a number and then subtract a number and then add a number and subtract a number. So same idea though. So okay, now this is an exercise for you to try. So go ahead and hit that good old pause button, and an opportunity for you to see how you're feeling with this new terminology: absolutely convergent, conditionally convergent, or divergent. Before you jump right into it, I do want to say kind of a tip, I guess. So when you're determining whether something is absolutely convergent or conditionally convergent or divergent, I tend to look at the absolute value one first, because if that converges, then you can just state that it's absolutely convergent and you don't have to test anything else. So that's my tip to you. Try doing the absolute value one first, and then seeing whether that converges or not, and then you can go from there. Okay, so welcome back, and let's see how that one went. Okay, so again, I gave you a little hint that if we went from 1 to infinity, so we're going to start by taking the absolute value. Here we go. So the absolute value, again, we know that n is positive, right? And so it's the -1 to the n minus 1 that is, again, that alternating factor that causes positives, negatives to alternate. And so when I take the absolute value of an alternating series, what I'm left with is essentially just that positive series, n over n cubed plus 1. So essentially what we're looking for now then is, does this series, this positive series, does this converge? If it does, then that means that the alternating series converges absolutely. Okay? If it doesn't, then we'll want to see if it maybe converges conditionally. So looking at this series, n over n cubed plus 1, if we want to know whether this converges or not, we need to kind of think back to all the tests that we've learned, right? So looking back, the divergence test I can tell won't work because this limit would end up being 0. And again, if the terms decrease to 0, that does not automatically mean that the series converges, especially for a positive series that's not alternating. Let's see, what else did we have? It's not geometric. It is not a p-series, but it is kind of similar to a p-series, isn't it? So when that happens, when it's similar to a p-series, you're usually going to use either the comparison test or the limit comparison test. So I always start to see if I can use the comparison test because it's easier. It doesn't require me to evaluate a limit. So to use the comparison test, I would want to compare this to, again, I like to kind of use a little placeholder so I don't have to think about the inequality just yet. So I'm going to say, okay, let's compare it to the similar p-series that this is. Adding 1 in the denominator is not going to make much of a difference overall, and so that means that this is similar to a p-series n over n cubed, which is equal to the series 1 over n squared. Okay, now I know that this p-series converges since the p-value is 2, which is bigger than 1. Okay, so now we're going to go back to this part here and decide which way our inequality sign, not which way it needs to go. It's only going to go one way to make a true statement, right? So this isn't about convenience. It's about what's true and what's not true. So in this case, notice again the addition of 1 in the denominator doesn't make a whole lot of difference. But the idea is that when I add 1 in the denominator, if I compare these denominators, I can see that the one on the left has a larger denominator, which means that it is overall going to be a smaller fraction. Again, if you want to, you can kind of do some side work over here and do, something like n over n cubed plus 1 is less than n over n cubed. You can cross multiply to get n to the 4th is less than n to the 4th plus n. Let me shift this over a little bit. Don't you wish you could do this on paper? There's definitely been times where I'm like, I'm out of space on paper, and it'd be very convenient to be able to just grab and shift everything over. So just cross multiplying, we end up with the inequality n to the 4th is less than n to the 4th plus n. That's true, isn't it? You could also simplify this by subtracting n to the 4th from both sides, and you would have 0 is less than n, which is basically saying that n is positive, n is greater than 0. That is also definitely true because n is going from 1 to infinity. So if you aren't quite sure, when you set up that inequality sign, definitely you can kind of come up here and do some double checking. Okay, so now we're going to think about whether that inequality sign is in our favor. And yes, it is, because we have shown that this series, the one that we're interested in, is smaller than a series that converges, right? So basically we're saying that it's smaller than, if you recall, this series converges to pi squared over 6, which is kind of interesting. It's a number that's a little less than 2. So this is smaller than that, so it has to also converge. Okay, so what we can do then is say something along the lines of, since the series 1 to infinity of n over n cubed plus 1 is less than the series 1 over n squared, and we know that the series 1 over n squared converges. Again, it's a p-series. This is my justification statement here. P-series with p equal to 2, which is greater than 1. Then by the comparison test, you are welcome to start abbreviating these, by the way. If you would like to use CT for comparison test, LCT for limit comparison test, AST for alternating series test, you're welcome to do so. By the comparison test, this series converges. And then I'm going to do kind of a semicolon because I'm going to start another sentence here that now I'm going to state my conclusion, which is the actual answer to this particular question. Since the absolute value of this series converges, then that means that this alternating series is absolutely convergent. So I would say something along the lines of, thus, because I like to be fancy, thus the alternating series, negative 1 to the n minus 1, n over n cubed plus 1, is absolutely convergent. And there we go. So again, the reason why we would start with looking at the absolute value first is because now I don't have to do anything else at this point. I don't need to check to see if this converges by the alternating series test, because I've already shown that it's absolutely convergent, so it's not going to be conditionally convergent. Which takes us to our next theorem. If a series is absolutely convergent, then that means that the series itself is convergent. I guess I kind of was using that assumption already, wasn't I? Let's go ahead and run through this, and then I can help that to justify what we just mentioned up here. That is why we don't have to go through whether that alternating series converges or not. So let's think about why that would be the case. So if a series is absolutely convergent, then that means that the non-alternating piece is convergent. So basically when we say that a series is absolutely convergent, this is basically saying that the absolute value, right, converges. That is, if we think of all the terms as being positive. And so again, if you think about that, if you think about the fact that if all the terms are positive and you add them together, you get convergence. If some of them are negative, all you're going to do is have a smaller sum, right? So if your series is alternating, for example, the alternating, I'll do n squared versus the series just 1 over n squared, right? So we know that this series converges to, again, pi squared over 6. This one also converges by the alternating series test. If you compare the terms, this is 1 plus a fourth plus a ninth plus a 16th, dot, 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 right? The alternating one is 1 minus a fourth plus a ninth minus a 16th plus dot, dot, dot. So it's pretty clear that this is going to be smaller than this, right? If you look at all the positive terms added together and it converges, then the alternating one is definitely going to converge because you're actually going to end up with a smaller sum in the end. So that's basically what this theorem is saying. But to give some more mathematical justification, as opposed to just making sense of why this would be true, let's actually run through a proof really quick. The proof is going to be, again, really fast. Notice there's not much space here. The proof is going to use the squeeze theorem. And essentially what we're going to do is we're going to look at the first statement here. It says if a series is absolutely convergent. So that is an assumption that we can go based off of. This is a result of that assumption. Okay, so if this series is absolutely convergent, then that means that this series converges, right? Okay. Now we're going to set up a squeeze theorem. We're going to look at these absolute values here. We're going to look at the series a sub n. Now keep in mind that a sub n could be alternating in some way. That is, some of its terms could be positive or could be negative. What we can do is we can set up an inequality, a between inequality, and we can say that this series is always going to be less than or equal to the sum of its absolute value of terms, right? So if a sub n was a positive series, then it's the equal to that would be true here. If there were some pieces that alternated, so maybe some were negative, then it would be the less than part, right? That would be true here. Okay, and we can also put a greater than or equal to here. So the series a sub n is going to be greater than or equal to if all the terms of the series were negative, right? Okay, this would be convergent to a negative number. This would be convergent to a positive number. And we know it's convergent and not divergent because we have already been told that a sub n, the series a sub n, is absolutely convergent. So we're basically just kind of pinning the series a sub n, the one that we're interested in here, between its absolute values because we know it's, again, absolutely convergent. And it's clear that this is convergent. We know it's convergent because, again, we were told that. And we know that this is convergent because you can just pull the negative sign out in front, right? And that also then is convergent. And so that means that this series must also converge by the squeeze theorem. again, pretty quick, straightforward proof, but it's always nice to kind of see, some different theorems that we've learned in the past at work. So let's move forward. Oh, a quick note here. A series being convergent does not imply that it is absolutely convergent, right? So we have it the other way around. If a series is absolutely convergent, then the series is convergent. But if the series converges, it doesn't mean that it converges absolutely, right? So consider the alternating harmonic series. That's a good example of that, because the alternating harmonic series itself converges, but the harmonic series does not converge. Let's take a look at another example. Determine whether the series sine of n divided by n cubed is convergent or divergent. And we're going to, as always, justify our conclusion as specifically as we can. So looking at this particular series, if I were to write this out, starting at 1, it would be sine of 1 over 1 plus sine of 2 over 2 cubed, which would be 8, plus sine of 3 over 3 cubed, which would be 27. I'll just go ahead and write one more out. Sine of 4 over 4 cubed, which would be 64. Dot, dot, dot. So I want us to kind of think about this one. Notice that the n cubed in the denominator is always going to be positive, right? But the numerator is going to sometimes be positive and sometimes be negative. Because if you think about the sine function, which is based on the unit circle, we can see that sine gives us the y coordinates, right? And so sometimes, basically, these are going to be numbers that alternate between -1 and +1. Sorry, let me rephrase that. They do not alternate between -1 and +1. They vary in value between -1 and 1, but not exactly -1 or +1. It actually will never be exactly -1 or +1, because notice that we're not going to have any pi over 2s or 3 pi over 2s showing up in here. It's just sine of 1, which 1 radian is roughly about here. That's going to be positive. Sine of 2, let's see, 2 radians should be, yeah, I think about over here somewhere. And then 3 radians, if you think of 3.14, right, as being pi, it's going to be just shy of that. So you can kind of see what's going to happen. Sine of 1, sine of 2, sine of 3 are all going to be positive in value. And then sine of 4 is going to now be down here. It's going to be negative in value, and sine of 5 and sine of 6 are also going to be negative. So this is not itself, this is not an alternating series. It might feel that way a little bit, because the terms are sometimes positive and sometimes negative, but in order for it to be an alternating series, to kind of come back up here, it needs to alternate like exactly. It needs to be one term, the previous term was positive, then the next term is negative. Positive, negative, positive, negative. So this one is not exactly an alternating series. It is also not a positive series. So it's kind of in its own little boat, and we can't quite use all the things that we've learned, like as far as we can't use the alternating series test. We can't use the comparison test or the limit comparison test because the terms of the series are not positive. That was one of the things we needed in order to use those. So it might feel like we might be a little bit stuck here, but don't worry. What we can do, again looking at this, is use this idea. The tricky part about this particular series is that sometimes randomly, sometimes the terms are negative or positive, but not consistently, right? So what we can do is we can consider the absolute value of the terms to now make this a positive series. And if this series that I've just put here, if this series converges, then that means that it converges absolutely, which means that this series converges. So let's see if that helps us. So when we do the absolute value, what we can look at is comparing it to maybe a p-series, because this is pretty similar to a p-series, isn't it? You've got the n cubed in the denominator. In the numerator, you're just going to have something, the sine of n part, that's going to be alternating in value between some numbers between -1 and +1, right? And so that means that this numerator here, this numerator, sine of 1 over n, is always going to be less than or equal to 1. I should say the absolute value part. Let me write it over here. Let's write this down here. The sine of n is always going to be a number between -1 and 1. The absolute value then is always going to be less than or equal to positive 1, right? Because if it's between -1 and 1 and I take the absolute value, then the largest that the absolute value of sine of n could be is positive 1. So what I can do then is write this inequality that this series is always going to be less than or equal to 1 over n cubed. Again, because the absolute value of sine of n is always going to be less than or equal to 1. Think of it this way. 1 is the largest that it could possibly be. So 1 is the largest it could possibly be. So now I've written this inequality, and I have a p series with p equal to 3, which is greater than 1. So this p series converges. And based on this inequality sign, that means that this series is also convergent by the comparison test. So I would write something along the lines of, since this inequality with the absolute value is less than or equal to this series, and we know that the series 1 over n cubed converges. Again, p-value is 3, which is greater than 1. Then by the comparison test, this series, absolute value sine n over n cubed, also, I'll just say converges. And then maybe over here, if I had a little bit more space, I'll do kind of be my extra sentence here. Since the absolute value of the series converges, then it converges absolutely. So this series that we were originally interested in, sine n over n cubed, also converges by that theorem that we just looked at. Okay. All right, so notice that we've got a lot of things going on. It's like, in this case, we needed to take the absolute value so that we could compare it to a positive series, in this case, a positive p series that converges. Given that inequality sign, we can state that the the absolute value series converges, and if the series is absolutely convergent, then the series is convergent. Okay, moving forward, hopefully you're feeling okay with this so far. Let's do a technology exploration. So consider determining whether the series n cubed over 3 to the n converges or diverges. Let's explore why the tests that we've learned so far are insufficient, and then let's use Desmos to investigate whether this series appears to converge or diverge, to just kind of give us an idea of how can we maybe approach showing that this series converges or diverges. Notice this one is not an alternating series. Okay, so let's start out with this is also a great opportunity for us to recap the tests that we've learned. The divergence test. The divergence test is not going to help us in this case because the limit as n goes to infinity of n cubed over 3 to the n would equal 0. That might not be, hopefully that's, I don't know, might not be 100% obvious, but 3 to the n is going to grow much faster than n cubed is. And so eventually these terms are going to be getting closer and closer to 0. So recall that if the limit of the terms is 0, that doesn't tell us anything. It doesn't mean that it's going to converge. Like 1 over n, right? Those terms go to 0, the harmonic series. Those terms go to 0, but the series diverges. So divergence test, not helpful in this case. I'll put a little X here. The next thing we learned was geometric series. And in this case, this is not geometric, right? I mean, we do have a geometric component, but then we also have this n cubed, and so it's not geometric. So I can't use like r equals this thing. P series? I'll put a question mark. Similar to, I mean, it has this piece, but it has also kind of a geometric piece. So it is not a P series. The integral test? Well, that's possible that we could do the integral test. It would be pretty complicated. You'd have to do n cubed times 3 to the negative n, and I believe you'd end up having to do integration by parts 3 times. and you would also need to know the antiderivative of 3 to the n, basically. So I think I'm going to write maybe, because I think this would work, but let's see if we can come up with something that's a little bit easier for us to use. What else have we done? The comparison test. Now if we were to compare, let's see, if we did the comparison test, I think I would probably compare it to that 3 to the n is going to be the kind of the dominating term. So I would probably compare this to 1 over 3 to the n, because then this is a geometric series 1/3 to the n, right? This converges. But unfortunately, looking at the inequality sign, the n cubed in the numerator is going to make this series larger, and so that means that this comparison test would be inconclusive. So that's not going to work. A lot of times when that happens, we would do maybe the limit comparison test, and so then we would look at the limit as n goes to infinity of n cubed over 3 to the n divided by the thing I'm comparing it to, which is 1 over 3 to the n. Feel free to, if you think maybe we could have compared it to something different, feel free to try that and kind of see. Okay, let's see if we evaluate this limit. I would get n cubed over 3 to the n times 3 to the n over 1. And notice I get the limit as n goes to infinity of n cubed, which is infinity. And if you recall, the limit comparison test is conclusive whenever the limit is a number between, I guess you could say a number between 0 and infinity, not including those numbers. So just any finite number that's positive, and that is not what happened here. So this is also inconclusive. It's not an alternating series, so we can't use the alternating series test. And so again, we're stuck. They're things that we've learned so far are relatively are insufficient. Again, the integral test, but that's a maybe, but it looks like it'd be rather complicated. So here's what we're going to do. We're going to kind of think about, let's use Desmos to kind of get an idea of whether this converges or not. Okay, so pulling up Desmos. Start graphing. Okay, so remember there's a few different ways we can do this. We can do a slider or we can do a table. I personally like the table because I feel like I can get a bigger picture of what's happening overall. We want to look at the nth partial sum of this series, starting at 1 and going to n. Okay, so what we're going to look at then is, let's look at the terms themselves, which were n cubed divided by 3 to the n, so we can kind of see what happens to the terms of the sequence. And then let's take a look at the partial sums. So remember, SUM pulls up the sigma notation. We do not want to use n for the index because we want n to be the upper bound of our summation, and that's what makes this the nth partial sum. So we'll do I equals 1, and then we'll do I cubed divided by 3 to the I. Okay, now don't worry about these warning signs. It's just telling you that your list is currently empty. I know. So I'm going to do 1, because that's where our series begins. 2, and then it'll just start to do autofill for me. And now I'm just hitting enter repeatedly to kind of see what happens. So notice that the terms of the sequence, n cubed over 3 to the n, are decreasing to 0, as we had expected when we were looking at this limit right here, right? Okay, so cool. Then let's take a look at the nth partial sum. The nth partial sum is increasing as we would expect it to, but it appears to be increasing within a certain bound. Let's see. I'm going to just kind of keep going, and I just kind of am seeing some more 9s, 4.1249999, and now Desmos is just going to start rounding because it's gotten so close to 4.125 that it's just going to go ahead and round it. Again, we can visualize this sequence and series. Well, essentially, we're visualizing the sequence of terms and the sequence of partial sums. So notice that the orange is the sequence of partial sums, and the green is the sequence for the terms themselves. So again, I have a touch screen, so I'm just going to use my fingers to kind of zoom out here to kind of see what's happening to the sequence. You could also go here and adjust the scaling accordingly right there. And yeah, you can see what's happening. You could do more if you wanted to, but it appears that the sequence of partial sums has a bound, and the bound appears to be 4.125. So I would say then, based on what we see here in Desmos, that the series seems to converge to 4.125. Okay. All right. So again, little exploration there, but now this doesn't justify it enough though, right? This doesn't tell us that the series definitely converges. It's just kind of a, it seems like it does, but we would want to be able to justify it a little bit more than that. So bring on a new test. So here's the idea with what we're going to eventually call the ratio test. Looking at this as an example, again, we can see that in the end, the 3 to the n is going to totally dominate over the n cubed, right? If you compare these things, let me go back here to Desmos just to show you what I mean by that. I can create another table where we can again look at, I'll just go ahead and do x for this one because I've already done n in the previous table. So if I look at x cubed versus 3 to the x for values of x, let's see. Whoa. Okay, so notice that they start off slow, kind of a tortoise hare situation, and then they're the same at 3, of course. 3 cubed is the same as 3 cubed. But then after that, you'll notice a very, very big difference in the exponential growth of 3 to the x versus just the, power growth, I'm not sure if that's what it's called, of x cubed. And so in the end, the 3 to the x, or 3 to the n rather, in the denominator is going to really take over, and this is going to start to look more and more like a geometric series. Recall that a geometric series converges, so let's look at geometric series in the first place, ar to the n minus 1, right, when n was 1 to infinity. This converged to a over 1 minus r when the absolute value of r was less than 1. This part's not so important, so you can kind of ignore that for right now, but I figured we'd throw that little reminder in there. So a geometric series converges when the r value, the absolute value of the r value, is less than 1. Okay, so that's something important for us to remember. And remember that is the case because, like, for example, like 1/2, 1/3, 2/3, 5/6, if I continuously multiply those together, then the terms of the series will approach 0. If I were to take 2 squared, 2 cubed, 2 to the 4th, right, 2 to the n, that would continue to grow. So this causes exponential decay as opposed to exponential growth. And so that's why we look at the absolute value of r being less than 1 in order to have convergence for a geometric series. Okay, so again, this series is not geometric, but for very, very large values of n, it will start to look like geometric series because of the fact that the 3 to the n is going to be the dominating term of n cubed over 3 to the n. So what we can do is we can look at, well, what happens to the ratio of consecutive terms? So recall that in a geometric series, the ratio of consecutive terms is always r. Again, that's in a geometric series. When you take one term and divide by the previous term, you will always get that common geometric factor of r. So the ratio test uses that idea in that if we look at the ratio of consecutive terms for larger and larger n values, this will start to approach, potentially, some limit L, which will basically be like what that geometric factor is. And if that is less than 1, then the series converges. Notice that since we're doing the absolute value here, then we can actually state with the ratio test whether a series is absolutely convergent and therefore convergent. If L is greater than 1, then remember that the geometric series diverges when the absolute value of r is greater than 1. So if L is greater than 1, then the series diverges. If L is equal to 1, the ratio test actually ends up being inconclusive. And we can talk a little bit about why that would be the case. I'm debating on whether I want to do that now or later. Well, let's just take a really quick example at, let's say, the harmonic series. Okay, so we know that the harmonic series diverges, right? If I use the ratio test on this, I would have 1 over n plus 1 over 1 over n. I'm not doing the absolute value right now because 1 over n would be positive for n positive. And notice that this would give me the limit as n goes to infinity of n over n plus 1. And that limit is 1. So I got 1 out of the ratio test for the series 1 over n, but the series 1 over n is known to diverge. If I do the same thing for 1 over n squared, I would have the limit as n goes to infinity of 1 over n plus 1 squared over 1 over n squared. So again, the n plus 1th term versus the nth term. And this would give me the limit as n goes to infinity of n squared over n plus 1 squared. And notice this would also equal 1. So we got 1 in both cases, but in this case, this series, the series 1 over n, I was going to use red actually. Sorry, my pen's not erasing. Come on, pen. There we go. The series 1 over n diverges. If I look at this one, the series 1 over n squared converges. Okay, so that's why the ratio test is inconclusive if L is equal to 1, because notice that we got L equal to 1 in 2 different scenarios, one of which the series converges, one of which the series diverges. So, inconclusive. Okay, so yeah, so essentially when that happens, we just need to try a different test that we've previously learned. Let's look at an example. We're going to look at the example that we used to kind of lead us into the ratio test, except now we're going to have this alternating component as well. Okay, so the ratio test again says that we want to look at the limit as n approaches infinity of the n plus 1th term divided by the nth term, and we're going to look at the absolute value of that. Okay, again, this is like if the absolute value of r is less than 1, then it converges. That's the idea here. Okay, so in this case, we would have, so when you're finding a sub n plus 1, just keep in mind that like a sub n, for example, is going to be negative 1 to the n cubed over 3 to the n, right? The next term, a sub n plus 1, would be, like, it's just like when we are plugging in 3 or 4 or 7 or whatever, right? We're plugging in whatever this is for n. And so that means in this case we're plugging in, anywhere we see an n, we're going to plug in an n plus 1. So this would be negative 1 to the n plus 1, n plus 1 quantity cubed, divided by 3 to the entire quantity n plus 1. Okay? That's going to be really important that we feel comfortable doing that as we go through the ratio test. Okay, all right, so that's our n plus 1th term divided by the nth term. And I'm going to show you some shortcut options as well, because as you can see, these oftentimes result in taking up a decent amount of space. Again, I wish I could do that on paper. Okay, so we have this limit then that we're looking at. This is the n plus 1th term divided by the nth term, and we're taking the absolute value. So notice as far as the absolute value goes, these two pieces are the alternating factors, and they are always just going to be positive or negative in sign. So we really don't have to worry about them because we're going to take the absolute value anyway. These are already positive, right? Because n is positive, so n cubed is positive. N is positive, so 3 to the n is positive. So I can basically rewrite this as the limit as n goes to infinity of, I'm going to basically do 2 simplification steps at once. I'm going to get rid of the alternating factors, and then I'm also going to rewrite this instead of the division of a fraction as the multiplication of its reciprocal. So we'd have n plus 1 cubed divided by 3 to the n plus 1 times the reciprocal of n cubed over 3 to the n, which would be 3 to the n over n cubed. Okay, so again, got rid of the absolute value. I guess that was really like 3 steps in one. got rid of the absolute value, got rid of the alternating factor because we took the absolute value of it, and then instead of dividing by a fraction, multiplied by the reciprocal. Okay, let's try to evaluate this limit. So what I'm going to do next is try to combine things that are alike. So I've got these two pieces here that are similar, and these two pieces here that are similar. So let's kind of group those together. I'm going to have 3 to the n over 3 to the n plus 1 times n plus 1 cubed over n cubed. You could have written that the other way, left, right, either one, doesn't matter. But kind of putting those together is going to allow me to evaluate this limit. Okay, let's take a look at this piece first. 3 to the n over 3 to the n plus 1. So simplifying this, I can think of this a few different ways. If you plug in a number for n, for example 7, you'd have 3 to the 7th divided by 3 to the 8th. Or 3 to the 11th divided by 3 to the 12th. All right, you can see that you're going to always get 1/3 out of this because the denominator is just going to have one more factor of 3 than the numerator is. Another way we can write that is this is 3 to the n divided by 3 times 3 to the n, right? The 3 times 3 to the n would create 3 to the n plus 1. So this cancels and simplifies to 1/3. Now this one, I can't really cancel anything, right? But I definitely can't cancel any n's or anything like that. I could expand everything, but it's actually going to be easier to not do that. And instead, I'm going to use the algebraic property that if I have a to the n divided by b to the n, then this is a divided by b to the n. So that means that we can write the n plus 1 cubed divided by n cubed as n plus 1 divided by n quantity cubed. From here, we would have a few options. We could either look at n plus 1 over n as n approaches infinity, and we can see that that approaches 1. You could use L'Hopital's rule. You could also rewrite n plus 1 over n as 1 plus 1 over n. I think that might actually be, I kind of like that. Let's do that. 1 plus 1 over n cubed, and then we can see that 1 over n is going to approach 0 as n approaches infinity, and so this gives us a limit of 1/3. Now let's think about what that means. So we looked at the ratio of the n plus 1th term over the nth term as n goes to infinity, and notice that we got 1/3 when we were done. And the reason why we got 1/3 when we were done is because of the fact that this this series is going to start to look more and more like a geometric series, specifically the geometric series 1 over 3 to the n, which notice has a factor of 1/3, right? 1 over 3 to the n is the geometric series 1/3 to the n, so the r value is 1/3. So it makes sense that we got 1/3 when we were done, because as n grows, like for larger and larger values of n, that's saying that the terms of this series are going to start looking more and more like the terms of the geometric series 1 over 3 to the n. Okay, so since that is less than 1, then that means that this series converges. Not only does it converge, but it converges absolutely. So I would say something like, by the ratio test, the series that we were interested in, n cubed over 3 to the n converges absolutely. Excellent. Okay, I think you're going to really like the ratio test. Let's do a few more examples. Okay, so with this one, let's determine whether the series n to the n divided by n factorial converges or diverges. Justify our conclusion as usual. Really quick though, sorry I moved forward, but since this converges absolutely, then remember that that means that this series also converges, and that was the one that we had just looked at that we thought looked like it converged to about 4.125. So I just wanted to point that out as well as kind of a closure for that particular example. Okay, so we are going to use the ratio test in this case. Again, it might not be obvious right now that the ratio test is going to be helpful. There's going to be a few factors that we look at when we are determining what test that we should use. Most of the time we're going to use the comparison test or the limit comparison test. when we see things that are similar to p-series, like this. And when we see things that are similar to a geometric series, or if we see factorials, we will tend to use the ratio test. And you'll see why as we go through this particular example. Okay, so we're going to do the ratio test. I'll go ahead and write that out. Okay, we're going to take the limit as n goes to infinity of, again, the n plus 1th term divided by the nth term. I'm going to go ahead and write that just for these first few examples that we do, but feel free to kind of skip writing that as you start to do more. There can be other things that you can skip as well as you start doing more and more examples. For example, like you could jump right to this multiplication by the reciprocal as opposed to doing the fraction divided by a fraction. That is, you could think of this as being a sub n plus 1 times 1 over a sub n. So you can think of it as a multiplication by the reciprocal if you want to, as a little shortcut. Okay, I think I'm not going to do the shortcut here, but maybe in the next one, just so that we don't skip too many steps when we're first starting out. Additionally, these terms are always positive, and so I wouldn't have to use the absolute value, but I'm going to in this particular case. So we're going to replace all of the n's with n plus 1 to start off to find our a sub n plus 1 term. So that would be n plus 1, that's our base, to the n plus 1, that's our exponent, divided by n plus 1 factorial, divided by, and I'll probably do some shifting here, divided by the nth term, which is n to the n over n factorial. I think it's going to get the infinity. There we go. Okay, and now we will go ahead and kind of simplify this a little bit. The absolute value, again, these terms are positive, so I really don't need the absolute value piece here. And so I'm going to go ahead and write this as n plus 1 to the n plus 1 divided by n plus 1 factorial times the reciprocal, n factorial over n to the n. Now, if you wanted to, this could have been basically like your very first step. If you feel comfortable with kind of doing all those steps in your head, you are more than welcome to do so and just kind of get right to this more simplified piece. Okay, so now that I have this, I'm going to go ahead and write this, again, kind of bringing together the things that are alike. So these are alike, and these are alike because they have factorials. And so I'm going to write this as n factorial, oops, sorry. There we go. N factorial, no, just doesn't want to be blue. N factorial divided by n plus 1 factorial, there we go, times the n plus 1 to the n plus 1 divided by the n to the n. All right, now we need to look at how to simplify this. Let's go ahead and start with the factorial piece here. So again, I'm going to kind of go off to the side here and think about how we would simplify n factorial divided by n plus 1 factorial. So we've had a little bit of exposure with factorials from sequences. I believe we haven't really just looked at them again since then. But remember that factorial is essentially just, like for example, 5 factorial is just saying take 5 times 4 times 3 times 2 times 1, right? So take that number and then multiply by all the previous whole numbers up until you get to 1. So n factorial would be n times n minus 1, the previous one, up until 3 times 2 times 1. I think I'm actually going to move this over here. And then n plus 1 factorial would be saying start with n plus 1 and now multiply by all the previous whole numbers. So the one that would come before n plus 1 would be n, and then n minus 1, and then up to 3 times 2 times 1. So notice what happens is this simplifies quite nicely because the n factorial cancels with this n factorial. So if you wanted to, another way you could write this is n factorial divided by n plus 1 times n factorial. And so notice that what happens is the n factorials cancel, and you're left with 1 over n plus 1. And now let's focus our attention on the other piece. So this one, it is n plus 1 to the n plus 1 divided by n to the n. Now I want us to think about how we could go about simplifying this. So this is kind of similar to the previous one that we did, where we thought of it as being, n plus 1 cubed divided by n cubed, we can think of as n plus 1 over n all cubed. Now that only works if the exponent's the same though, right? So this rule here. In this case, the exponents are not exactly the same. One of them is an n plus 1 and the other one is an n. But what I can do is I can think of the n plus 1 exponent as being n plus 1 times n plus 1 to the n, right? This would create, think of that as the first power, and then, right, we would add the exponents together, making that n plus 1 exponent. Divided by n to the n, and now I could write this as the quantity n plus 1 times the quantity n plus 1 over n all to the n. There's a lot of n's going on, aren't there? Okay, so hopefully you felt okay with that algebra. Now we're going to kind of rewrite, now that we've kind of gone through some algebra and simplification. So again, this piece simplified to 1 over n plus 1. And then this piece simplified to n plus 1 times the quantity n plus 1 over n to the n. Now notice we get an additional simplification here, that 1 over n plus 1 times n plus 1 is going to just be 1. And so I end up getting the limit as n goes to infinity of n plus 1 over n to the n. A few ways we can take a look at this one. I think I'm going to actually rewrite this as 1 plus 1 over n to the n. And notice what happens with this one is that as n approaches infinity, the base approaches 1 and the exponent approaches infinity. Now you might look at 1 to the infinity and go, oh, that should be 1 because 1 to any power is 1. And you're right, 1 to any power is 1 as long as that power is finite. Like 1 to the 500 billion is 1. But 1 to the infinity is a different story. And the reason why it's a different story is because if you imagine this base is not exactly 1. It's just approaching 1, right? And so if you were to look at, like, for example, 1.000001 even, to a very, very large power, this could start to approach, this could start kind of grow without bound. It could start to approach a number. We don't really know. This 1 to the infinity is an indeterminate form, which hopefully you've looked at before. We actually have proved in L'Hopital's rule, I'm not sure where you may have taken Calculus 1 or Calculus 2. At PCC we teach L'Hopital's rule in Calculus 2. This is a limit that you should have seen in that course at some point, probably, hopefully. And this limit comes out to be, well, if you don't remember, another thing we can do is we can resort back to Desmos and look and see what happens. So let's actually put in, maybe I'll put this in, 1 plus 1 over n, or x rather, raised to the x. And I'm going to get rid of this column because we really don't need it. Okay, and then we'll see as we put in larger x values. Get rid of these. I wonder if I should have just done a oh, why are there so many in here? I wonder if I should have just done a blank screen, but oh, there we go. Okay, so looking at larger values of x. Okay, let's speed up this process a little bit. 1,000, 10,000, 100,000, 1,000,000, 10 million, and now I'm not really seeing it change too much. 2.718. Oh, that's that. I think I just broke Desmos with that one because that 5 should not be there. So it looks like this is approaching 2.7182821, which is the decimal approximation for e. So this limit is e. Now again, you can show this using L'Hopital's rule. I'm not going to go through that process because it's quite an extensive process where you use logarithms and then you convert this indeterminate power into an indeterminate product, which then gets turned into an indeterminate quotient, and then you're allowed to use L'Hopital's rule. What I can do is maybe link to a video if you are interested in seeing how this limit process comes out with the use of L'Hopital's rule. I'll go ahead and link to that. Okay, so we get E. What does that mean? Well, the fact that we got E, and E is about 2.718, which is bigger than 1, then by the ratio test, that means that this particular series diverges. So we'd say something like by the ratio test, this series n to the n over n factorial diverges. Now, you can actually use the divergence test on this particular one also, because the limit as n goes to infinity of n to the n over n factorial is infinity. That is, n to the n grows faster than n factorial does. We actually showed that, well, we showed in sequences, we showed that the limit as n goes to infinity of n factorial over n to the n equals 0. Right, and we used the squeeze theorem to show that. You can refer back to that section if you'd like. And so that means then the reciprocal of that should approach infinity. If n factorial over n to the n approaches 0, then n to the n over n factorial will approach infinity as n approaches infinity. So you can also use the divergence test in that particular case. Okay, moving forward, we have one for you to try now. So this, notice, is an alternating series. It has a factorial involved, and so this will be great practice for you to get a little bit more comfortable with factorials and the ratio test. So go ahead and pause, and then come on back after you feel like you've gotten some good exposure to this particular problem. Okay, welcome back, and we're going to go ahead and take a look at this one. So we're going to use the ratio test. And we will go ahead and take, I think this is where we could maybe start to do some simplification, or some step skipping, rather. So one thing we can look at is the n, so we're looking at the n plus 1th term. N plus 1th term. Now keep in mind that when we do the n plus 1th term, right, we're replacing n with the quantity n plus 1. So in this case it would be 2 times n plus 1. It won't be 2n plus 1, but it will be 2 times the quantity n plus 1, which we'll simplify in just a second. Okay, I'm going to multiply then by the reciprocal of the a sub nth term, which would be 2n factorial divided by negative 1 to the n. Okay, again, these two pieces here, these are the alternating factors, and so we can go ahead and simplify those. Another option is this does simplify to negative 1, doesn't it? Because you have negative 1 to the n plus 1 divided by negative 1 to the n. That will always result in a value of negative 1. So we're basically taking the absolute value of that, and now we're taking the limit as n goes to infinity of 2n factorial. And actually I can get rid of the absolute values now, because n is positive, so n factorial, well, factorial is always positive. And then this is 2n plus 2 factorial. Okay, here we go. We're going to try to simplify this factorial. And let's just go ahead and expand it out, and you can kind of see what things are going to end up canceling. So you can also, if you're like, oh, I feel okay with n factorial, but 2n factorial, I'm not quite sure how that works, feel free to just pick a value for n. If you pick an n, like for example, n equals 5, then you would end up having 2 times 5 factorial divided by 2 times 5 plus 2 factorial. That would be 10 factorial divided by 12 factorial, right? So then you can see this would end up being 10 times 9 times 8, dot, 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 up until 3 times 2 times 1. The denominator would be 12 times 11 times 10 times 9, dot, dot. So this is a better, helps to give you an idea once you're working with the numbers to see what's going to maybe happen. I see that the 10 factorial is going to cancel with the 10 factorial, and I will end up with 1 over 12 times 11 in this case. Okay. Now this isn't enough to show any sort of simplification, but this is to help make sense of what is being represented here. Okay, so now that we feel pretty confident about what this 2n factorial is telling us, we can write this out as 2n times the previous thing, which would be 2n minus 1, times the previous thing, which would be 2n minus 2, times dot 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 up until 3 times 2 times 1. Divided by, now in the denominator I would have 2 to the n plus 2 times the previous one, which would be 2 to the n plus 2n plus 1, and then the previous one, which would be 2n, times dot dot dot. Actually, let's do one more so that we can kind of see. So 2n, the one before that would be 2n minus 1, 2n minus 2, times dot 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 times 3 times 2 times 1, just so we can kind of see some common factors up in that between the numerator and the denominator. So I'm definitely seeing that. I see we've got 2n factorial here, and then 2n factorial here, and so what we'll end up being left with is 1 over 2n plus 2 times 2n plus 1. And notice that that's relatively consistent, well, is consistent with how we simplified when n is 5 also. So again, if you want to make sense of it, pick some number for n and kind of see what ends up happening. Okay, now this limit is pretty easy for us to evaluate because the numerator is just 1. The denominator has n's. It's going to increase as n increases, and so the overall fraction is going to approach 0. Now looking back up at the ratio test here, we can see that again, as long as the L value is less than 1, then we have convergence, and last time I checked, 0 is less than 1, and so that means that this particular series converges. So we just want to do some sort of conclusion, something along the lines of, by the ratio test, this series, negative 1 to the n over 2n factorial, converges, and I'm going to actually go one step further and say that it converges absolutely. Now I just realized, you know, what's kind of interesting is that it says determine whether the series converges or diverges. Now notice that this is an alternating series, and so you actually, to answer this particular question, let me put a little underline here, to answer this particular question, technically we could have just done the alternating series test to answer this question. So where b sub n is 1 over 2n factorial. So it's clear that this is positive, and it is decreasing because only an n is in the denominator. And we know that the limit as n approaches infinity of 1 over 2n factorial equals 0. So by the alternating series test, this series converges. That, again, is sufficient for answering this particular question. If we want to go a step further, or if the question had stated determine whether the series converges absolutely, then we would have definitely wanted to do the ratio test either way. So good practice no matter what. Let's move on to last one here, example 5. Determine whether this series converges or diverges. Justify your conclusion as specifically as possible. Okay, so notice with this one, I've got 1 over root n squared minus 1. I'm just going to show you what happens if we were to do the ratio test. Let's try the ratio test. We're going to take the limit as n goes to infinity of the n plus 1th term divided by the nth term. Now notice I'm leaving out the absolute values because the terms of this series are positive, so I don't really need the absolute value piece. And writing this in a simplified form, I would have limit as n goes to infinity, 1 over root n plus 1 squared minus 1 times the reciprocal, which would be root n squared minus 1 over 1. So this could be written as the limit as n goes to infinity of the square root of n squared minus 1 over n plus 1 squared minus 1. Okay, and then I think probably what I would do here is I can use the continuous property that square root is a continuous function. So this is the square root of the limit as n goes to infinity of n squared minus 1 over n plus 1 squared minus 1. It might be obvious to you that this limit is going to end up being 1, but we can go ahead and use L'Hopital's rule as well, just to make sure we're really justifying that. That would be 2n over 2n plus 1. That's using the chain rule. Notice we still get an infinity over infinity, and I would use L'Hopital's again. Root limit n goes to infinity, and now it would be 2 over 2, which now we can see the limit is definitely 1. Okay, so notice if you use the ratio test, what we end up having is, well, unfortunately it's inconclusive. Right? When the ratio test results in 1, we end up having an inconclusive result. So I'm actually going to move this over here because we need to do a little bit more since the ratio test did not work. Okay, so let's see, what should we have done instead? So instead, notice this is somewhat similar to a p-series. Let's try the comparison test. So again, this series, 1 over root n squared minus 1, is similar to the series 1 over root n squared. And because of the subtraction of 1 in the denominator, that makes the denominator smaller, which makes the overall fraction larger. So my inequality sign would go this way. This series is equal to, well, the square root of n squared would be n. So this is equivalent to, I'm comparing to the harmonic series. The harmonic series, again, is known to diverges, harmonic series. And notice the inequality sign is going this way, and so that is saying that this series is larger than a series that diverges. So that means that that series must also diverge. So since this inequality is true, we need to start at 2 though, so we don't have division by 0. Root n squared minus 1 is greater than the harmonic series. And we know that the harmonic series diverges, harmonic. Then by the comparison test, this series that we were wanting to know about, starting at 2 though, also diverges. Now, if this had been a plus sign instead of a minus sign, my inequality sign would have gone the other way if this was a plus. So just as a reminder, if that was the case, we would need to use the limit comparison test instead. So if it was an 1 over root n squared plus 1, my inequality sign would have been less than a divergent series, which is inconclusive, so we would have used the limit comparison test. So notice that the ratio test didn't really work very well for that, did it? And it's not going to work very well for any p-series. You're pretty much going to always get the limit being 1 if you try the ratio test in a p-series. So just as an extra note here, a tip, the ratio test is going to be best used if the series has geometric components, like an r to the n, like 2 to the n or 10 to the n or 1/3 to the n, any sort of geometric component, and or a factorial component, like n factorial, 2n factorial, that kind of thing. The test does not work well for series that have only a p-series component, like n to the p, like in this case, p-series component of n squared. Okay, I hope you enjoyed the ratio test. It's one of my favorite tests. You'll see, again, it works best with geometric components and factorial components. So anytime you see those, think ratio test.